All right, so thanks a lot for the invitation. It's nice to be back in Fayetteville. Looking forward to the bed races. So everything I'll be talking about today is joint work with Steven Sibek. And just to start, I'll say, over the last couple of years, we've been defining invariants of contact manifolds with boundary in different Floer homological settings. And the motivation was to use the various features unique to each of these different settings to prove new results about contact structures. So I'll talk about a couple applications, but I'll focus on a particular application of our instanton Floer contact invariant. And the idea being that the sort of unique thing about instanton Floer homology is the connection that it makes with the fundamental group of a manifold. So the hope is to use that to prove results relating the contact geometry of a manifold and its fundamental group. So first, I'll tell you a little bit about where these various contact invariants live, and then about some of their formal properties. So to the first point, where do they live? Well, briefly, a contact manifold with boundary, you can think about it as a sutured manifold, and then the invariant is a class in the Floer homology of the sutured manifold. So maybe first, let me remind you what a sutured manifold is. So for us, a sutured manifold will be a compact, oriented three-manifold, closed, with a decoration, so an oriented multi-curve on the boundary of M. And this is what's called the suture. And the manifold in this decoration have to satisfy a few properties to qualify as a sutured manifold. So one is that M has no closed components. The second is that every component of the boundary of M contains part of the suture. Another way of phrasing that is that pi 0 of the suture surjects onto pi 0 of the boundary. And maybe the most important thing is that if we look at the complement of the suture in the boundary, so this curve, well, it divides the boundary into two subsurfaces, R plus and R minus, with the property that the boundary of R plus is equal to this oriented curve, and that's minus the boundary of R minus. And the last condition is the so-called balance condition, which is that we want the Euler characteristics of R plus and R minus to be the same. And I'll explain later why this is an important condition. So first, let me just maybe draw some examples, some typical examples. So one is, given a knot in a three-manifold, we can form a sutured manifold by simply removing the knot, looking at the complement. And I'll draw this. I'll pretend the knot is just the unknot for simplicity. So I've removed a neighborhood of the knot, and the sutures that I put on the boundary are these oppositely oriented meridians. And I'll denote that sutured manifold by y of k. So given a closed three-manifold Y, or any three-manifold, well, a closed three-manifold, let's say, we can also remove a ball, look at the exterior, right? And this becomes a sutured manifold once I decorate this sphere boundary component with this oriented equator. So by the way, in this case, the two subsurfaces are R plus and R minus, and R plus and R minus. And maybe the last example I want to talk about is, suppose we have a surface, so a compact surface, suppose it's connected, and look at the product of the surface with an interval, and decorate the boundary with copies of the boundary component of the surface, so boundary of S cross 0, 1. So this looks like So here's my surface S. And I thicken it up. And the suture in this case is just the boundary of S times 0. And you can see that this curve, or in general a multi-curve, if the surface has more than one boundary component, will divide the boundary of this handle body into two pieces, right? This sort of, the part you see here is like R plus, and the part on the other side is R minus. So these are some classic, or simple examples, but important examples of sutured manifolds. And so I mentioned briefly that to a sutured manifold, you can associate a floor homology theory in various contexts. So floor homology. And the sort of relevant settings for this talk will be so the Heegard floor setting, the monopole floor setting, and the instanton floor setting. So given a sutured manifold M gamma, I can associate these three groups in these three different floor homological settings. Sutured Heegard floor homology, which I'm writing in this way, was defined by Andras Juhas. And it's defined using, as is everything in Heegard floor homology, Heegard diagrams, counts of holomorphic disks. The monopole floor and instanton floor invariants of sutured manifolds were defined by Kronheimer and Rufka. Using the tools in gauge theory, in monopole floor homology and instanton floor homology. And the idea there, as I'll elaborate on later, is to take your sutured manifold and embed it in a closed manifold, and then apply sort of the construction of monopole floor homology and instanton floor homology for closed manifolds. So we take these sutured manifolds and form closures, which I'll talk about later. So I thought it might be interesting, or helpful at least, to describe what these groups look like for these three examples that I've listed here. So if you look at the complement of a knot with these sutures and compute its sutured Heegard floor homology, that's actually just isomorphic to what Shea was calling the knot floor homology of K and Y. That's the same thing, turns out. The sutured Heegard floor homology of the complement of a ball is isomorphic to just the sort of ordinary floor homology of the closed three-manifold, HF hat of Y. And for this very simple product sutured manifold, it's just isomorphic to Z. Okay, as rank 1. In the monopole floor case, well, you get something here that is not related to anything that was really defined previously. If you remove a ball, you get an invariant that in the monopole floor world is called HM tilde of Y. And in fact, we actually know that these two things are isomorphic by work of Taubes and others, Kalangajini and Honda, Kuhan, Lee, and Taubes. And again, in the case of a product sutured manifold, your sutured floor homology is rank 1. In the instanton floor world, well, for the sutured knot complement, what you get is actually isomorphic to another invariant of knots in instanton floor homology, also defined by Kronheimer and Rufka, called singular instanton knot homology. And if you've been following the subject, maybe you know that this is the theory that Kronheimer and Rufka relate to Kovanov homology in their proof that Kovanov homology detects the unknot. So they show that there is a spectral sequence from Kovanov homology to this theory, and then in fact they use the fact that these two things are isomorphic to show that Kovanov homology detects the unknot. So, it's not so clear how what you get in this case is related to any of the invariants in Heegard flow homology or monopole flow homology. It's maybe conjectured that what you get here is isomorphic to the Heegard flow homology of Y tensor C, but that's not known right now. For the product sutured manifold, again, you just get something of rank 1. Okay. So this is the setting we're working in. So, as I said, starting with a contact manifold with boundary, you should get an element in the sutured flow homology. Well, okay, so I said that a contact manifold with boundary is naturally a sutured manifold. So maybe that's the first thing I should explain, now that we've defined sutured manifolds. And the types of contact manifolds with boundary we'll study are contact manifolds with what's called convex boundary. So contact manifolds with convex boundary. And so what are these? These are, contact 3 manifolds such that there exists a vector field V, which is transverse to the boundary of M, whose flow preserves the contact structure. Okay, that's the convexity condition on the boundary of M. And given such a manifold with contact boundary, you can define a convex boundary. You can define a multicurve on the boundary of M by looking at the points on the boundary where this vector field V actually lies in the contact planes. Okay? And it turns out that this is a multicurve on the boundary of M. And in fact, M together with this multicurve is a sutured manifold. So that's what I meant when I said that manifolds with boundary are sort of contact manifolds with boundary are sort of topologically, naturally sutured manifolds. And I should say that this in contact geometry, this is called not a suture, but the dividing set. And this dividing set essentially determines the contact structure near the boundary of M, which is useful if you're trying to think about how to glue contact manifolds with boundary together along their boundaries. As long as you glue in such a way that the dividing sets match up, then you know that your gluing is sort of a contact geometric gluing. So that's the nice thing about studying contact manifolds with convex boundaries. Okay. And so we'll generally encode this information in a triple. So we'll encode the manifold, the contact structure, and the dividing set. And given such a thing, you can define, as I've said, classes in the associated sutured flow homology groups. And for various techniques, you have to reverse orientations. So you get a class in the sutured Heegard flow homology, a class which I'll denote CHM in the sutured monopole flow homology, and a class CHI in the sutured instanton flow homology of the associated topological manifold. And these are invariants of the contact structure in an appropriate sense. So this was defined by Handicke-Zesmatic, this contact invariant, using open books and the Giroux correspondence between contact structures and open books. And these two invariants were defined by myself and Stephen, using a mixture of things. So to define the monopole Floer contact invariant, we didn't actually use the Giroux correspondence. To define the instanton Floer contact invariant, we did use the Giroux correspondence. And I'll describe in a bit, hopefully, how these things are defined. In all three cases, one thing you can show is that these classes vanish if the context structure is over-twisted. Okay, so if your contact element is non-zero, then you know that the contact structure is tight. And as Shay mentioned, this has been a powerful way of proving tightness of contact structures. Was there a question? Was that?
Do they agree?
Yeah, so that was what I was going to say next. Don't apologize. So let's see, maybe I should put this over here. Well, okay. The theorem, so recently actually, Stephen and I, and actually, using the work of Taubes and Kalin, Gagini, and Honda. Uh-oh. Okay. Showed that these two essentially are equivalent. In other words, there exists an isomorphism from sutured Heegard-Floer homology to sutured monopole Floer homology, which sends the Heegard-Floer contact invariant, or identifies the Heegard-Floer contact invariant with the monopole Floer contact invariant. And this has a couple nice applications. For one thing, it allows you to show that this contact invariant in Heegard-Floer homology is well defined without resorting to the Giroux correspondence, because we know that this one is. And another application, and my favorite application, falls along the lines of what I was talking about in the beginning. We can sort of use this isomorphism to port advantages of the monopole Floer theory to the Heegard-Floer side. And so on the Heegard-Floer side, there are these combinatorially computable invariants of Legendre knots. And what we can do is we can use this isomorphism and properties of the monopole Floer invariant to show that these combinatorial Legendrian invariants in HF are functorial with respect to Lagrangian concordance between Legendrian knots. So what that means is that if you have a Lagrangian concordance between two Legendrian knots, then there's a map on knot Floer homology sending this combinatorial Legendrian invariant of one to the combinatorial Legendrian invariant of the other. So these Legendrian invariants provide interesting obstructions to the existence of Lagrangian concordances between Legendrian knots. But we really need this isomorphism in order to conclude that. John?
Is there an ambiguity in the monopole portion?
Yeah, so I guess when I say that when I say that this shows that this is well defined without the Giroux correspondence, what I really mean is that the vanishing or non-vanishing of this class is well defined without the Giroux correspondence. Yeah, so I think that's what you were getting at, right? Oh. Yeah, there is a sign ambiguity, yeah. There's also, yeah, okay, I see, yeah. There's also a sign ambiguity. So it doesn't prove nicer things. But, okay. So that's, an application of, oops. of these monopole floor contact invariants. As I said, I'd like to focus on the instanton floor contact invariant. And the main theorem of the talk, which is something we conjectured in our original paper, but now believe we've shown, is the following. So suppose Y is the boundary of a four-manifold X, and J1 through Jn are Stein structures on X with different Chern classes. And in fact, we want that the first Chern class of Jm is minus the first Chern class of Jn is non-torsion for all m not equal to n. Okay, and so these Stein structures on X induce contact structures on Y. So let C sub I be the contact structure on Y induced by J sub I. Then what we can show, so what we can do is we can restrict each of these contact structures to Y minus our Darboux ball. Right. So now we're in the setting of sutured manifolds. So we can talk about our contact invariants. And in fact, the result is that if we look at the instanton floor contact invariants of these different contact structures, I said they're N, oops, M, K maybe. These contact invariants are linearly independent. Linearly independent classes in the sutured instanton floor homology of Y with a ball removed, minus Y, ball removed. Okay? And so in particular, what that tells you is that the rank of this instanton floor group is at least N. Okay. So I should say that this result is the analog of a theorem of Olga that was proved in the Heegard floor setting. And maybe, well, it is at least consistent with this conjecture that the instanton floor homology of this manifold should agree with, at least in rank, with the Heegard floor homology of the manifold. So our interest in this theorem is that, well, as I said, instanton floor homology is related, or it's defined, in particular, it's defined in terms of representations of the fundamental group of the manifold into SU2. So the hope is that this theorem should allow you to say something about Stein structures, the relationship between the different kinds of Stein structures you can have on a four manifold with boundary Y and the fundamental group of Y. And it does. So there are several interesting corollaries you can derive from this theorem. Maybe the one that I'll focus on, which is the simplest to state, is the following. So if Y is the boundary of X, is an integer homology 3-sphere, and there exists a Stein structure J on X with non-trivial Chern class, okay, then there exists a non-trivial homomorphism from the fundamental group of Y to SU2. So, sorry? Okay. Is there a spray? Oh. Let's see. I don't need it? Oh, yeah. All right, so what I'd like to do actually is, and just because I think it's sort of neat, I'd like to explain how this corollary follows from the main theorem. Let's go through the idea of the proof. Okay, so how do we prove the corollary? Oops. Proof of the corollary from the main theorem. So suppose the conditions are met. So C1 of J is non-zero. And consider the conjugate Stein structure. So then C1 of J bar, well, it's equal to minus C1 of J. And so that implies that the difference is twice C1 of J, which is non-zero. So we're sort of in this situation here. Well, actually, this is, we need non-torsion there, but actually this implies non-torsion. Hence, the difference is actually non-torsion. And the way you see that is, well, you think, so the fact that Y is an integer homology 3-sphere implies that H upper 2 of X is isomorphic to H upper 2 of X rel Y. So just thinking about the long exact sequence of the pair. And then we know that this is isomorphic to H lower 2 of X by Poincare duality. And this is non-torsion since X is, well, it admits a Stein structure, so it can be built from 1 and 2 handles. Okay, so H lower 2 isn't torsion. That implies that H upper 2 isn't torsion. So as long as this difference is non-zero, it's non-torsion. Okay. So great. So that implies that by the theorem, that the rank of the sutured instanton full homology of minus Y with the ball removed is at least 2. Okay? But in fact, you can show that if you the instanton full homology of Y with a ball removed is actually the same as the instanton full homology of Y with an unknot removed. And as I said before, that's equal to the rank of this other version of instanton full homology, which makes a more direct connection with the fundamental group. Okay. So the upshot is that the rank of this is greater than or equal to 2. Okay. So remember that. So now I claim that there exists an irreducible homomorphism, an irreducible representation of the complement of the unknot into SU2, sending the meridian to I. So SU2 you can think of as the the quaternions, unit quaternions, right? So I claim that there is an irreducible homomorphism sending the meridian to I. There are always homomorphisms sending the meridian to I. The claim is that there is an irreducible one. Okay, so how do we show that? Well, suppose not. Then every such homomorphism is reducible, which actually implies that it has image in U1, essentially. So it's abelian. So what that means is that then rho factors through the first homology. So rho factors through H lower 1 of the complement, which of course is just isomorphic to Z. And so what that and we're requiring that it send a meridian to I. So it sends a generator to I. Well, there's only one homomorphism which does that, right? So there's a unique reducible. Okay. So if there's no irreducible, well, let's study the reducibles. And in fact, there's a unique reducible. And this reducible homomorphism then is the sole generator of the chain complex, of a chain complex that computes this instanton Floer group. So this instanton Floer homology is essentially what you're doing to compute it is you're doing Morse homology on the space of connections of some SU2 bundle over the complement of U with respect to the Chern-Simons functional. And the critical points are flat connections, which correspond to representations of the knot group to SU2. And actually, you have this sort of holonomy condition that needs to be satisfied as well. And this unique reducible is always a non-degenerate critical point, it turns out. So you don't have to perturb the Chern-Simons functional or anything. You actually have, your Morse complex. There are no irreducibles, you're assuming. And so that's it. And so that would imply that this thing has rank 1. But that's a contradiction, right? Because we've shown, due to the existence of these various the Stein structure, that it has rank greater than or equal to 2. Okay? So, great. So we've proven this claim. It has to be some irreducible homomorphism from the complement to SU2 sending a meridian to I. All right. Well, so rho is some, what is the fundamental group of the complement of an unknot? It's just the fundamental group of Y, the free product of that with Z, right? And so we have this homomorphism to SU2 sending M, the generator of this Z factor, to I. And so that implies, and it's irreducible, so that implies that the induced homomorphism, which I'll call rho Y, from pi 1 of Y to SU2 is non-trivial. Right? If the restriction from here to here were non-trivial, then this would not be irreducible. Right? So that's the proof. You have some non-trivial homomorphism of the fundamental group to SU2. Okay. If you're a rational homology sphere? So yeah, so you can say things about rational homology spheres also. In fact, here's something you could say. You can say, if you have a rational homology sphere, and the order of the first homology is less than 5, and you have more than 5 Stein structures, then there has to be an irreducible homomorphism. The sort of key, and what becomes harder when you're away from the integer homology cases is, well, if you assume you have no irreducibles, then everything is, an abelian representation. But you have to show that those abelian representations are all non-degenerate for the unperturbed Chern-Simons function. So you have to think a little bit. And in the case that the order of the first homology is less than 5, less than or equal to 5, you can show that. So yeah, you can say other things for rational homology 3 spheres. What I just told you is just one example. But this is maybe the most satisfying. All right. So, okay. Yeah. That's another great question. It's hard to say. So the problem is, in general, you don't know how much an irrep contributes to the instant-on floor homology because of these degeneracy issues. Like ideally, and maybe generically, an irreducible representation should contribute 2 to the rank because you'll have this for each irreducible representation. You should have this like circles worth of critical points, and so when you perturb the functional a little bit, that'll contribute 2. But you need to know that that circle of critical points is non-degenerate in the Moore spot sense, and when you can do that, when you can't do that is not clear to me, at least. But yeah, that's sort of the idea, right? I mean, this should constrain the number of and types of homomorphisms. All right. So maybe let me give you an example of something we could actually apply this corollary to. So for example, look at the trefoil, and what do we want? Some other 2n torus knot, do -1 surgery on here, -2 surgery on here. This is an integer homology 3 sphere, as you can see from the linking matrix. And in fact, this meets the hypotheses of the corollary. So in other words, you can show that this manifold is the boundary of a 4 manifold, admitting a Stein structure with non-vanishing Chern class. And the way you do that is you sort of, you just Legendre realize these curves. And then, well, you have something. Oops. Okay. I don't want to draw the rest of it. But the point is that, this has TB, well, Rieth minus half the number of cusps. So 3 minus 2 is 1. Good, right? Thank you. And if I stabilize like this, now it has TB 0, and so topologically -1 surgery is Legendrian, TB -1 surgery on this. And the thing is that this component has non-trivial rotation number now, and so what that means is that the first Chern class of the Stein structure will evaluate on a certain second homology class non-trivially. Okay. And this is some, the 4 manifold. Oops. It will be negative definite. Okay, so here's just a very simple example. There are millions it's very easy to construct examples. +1 surgery, yeah, should, yeah. So yeah, so actually that brings me to my next question. So in light of this corollary, you can ask, actually, is it the case that if y is not S3, then there always exists a non-trivial homomorphism from pi 1 to SU2? And so, I mean, is this corollary sort of, in a way, obviously true without relying on the theorem? I think this is probably a really hard question. So we've known for a while that the answer is yes. In certain cases, so for example, when y is not an integer homology 3-sphere, the answer is automatically yes. If y is not, well, then y admits a non-trivial representation. That's an easy exercise. So it was shown that the answer is yes when y is a Seifert fibered space. And this is a result of Fintischl and Stern from 90, when they used some of the earliest versions of instant on-floor homology to compute the invariants of Seifert fiber spaces. And actually, one thing that's interesting is that we can easily reproduce their result, reprove their result using our corollary. So if you have an integer homology Seifert fibered space, and it's not sigma 235 or sigma 237, then you can just very, very easily show that the conditions here are met. So it follows immediately. Let's see, for 1 over n surgeries on non-trivial knots, the answer is yes. This is a result of Kronheimer and Mrövka. I don't know why I hyphenated Kronheimer's name. And also, if y is an integer homology 3-sphere with a symplectic filling, with b plus greater than or equal to 1. And this follows from, I don't think it's actually written down anywhere, but it's easy to show that this is true by patching together results of Kronheimer and Mrövka, the sorts of techniques they use to prove the property P conjecture, along with certain non-vanishing results for Donaldson invariants on symplectic manifolds. They're due to Stephen. Okay, but maybe I should note that this is a filling that's not positive definite; it's a negative definite filling, so it doesn't actually fall under that classification. All right. So good. So that's the main thing I wanted to present. I'm almost out of time, so I don't think I'm going to be able to tell you how these sutured floor homology groups are constructed and how our invariant is defined and then how we prove the theorem. But let me maybe just say, I can do that. Well, I can do that. I can explain that to anyone after and be happy to. But let me just explain very, very briefly the idea behind the proof of the main theorem. Maybe explain is too generous. So the idea behind the proof of the theorem is roughly the same as the idea that Olga took advantage of in the Heegard floor setting, which is to embed your Stein manifolds into closed symplectic manifolds. And then use a result of Taubes on the Seiberg-Witten invariants of closed symplectic manifolds. Namely that they vanish except for the canonical class of the symplectic manifold. And what you can do is you can show that these Seiberg-Witten invariants of the closed symplectic manifold actually sort of factor through the contact invariants of these different contact structures on Y, which is some hypersurface in this closed symplectic manifold. And yeah, so that's more or less how you do it. Or that's how Olga proved her result. It's trickier in the instanton floor case because it's not anywhere near as obvious how to embed, in defining these instanton floor invariants, first of all, to define the instanton floor invariant of Y minus a ball, we have to use this closure procedure, as I discussed before. And so the sort of closed manifolds you're working with are not really Y. And the Stein manifold you're working with, the Stein filling is not really the Stein filling. So you have to think a bit harder about how to embed sort of the analogous thing into a closed symplectic manifold. And then, of course, you're working in the instanton floor world. You're not working in the Seiberg-Witten world. And so you need a result about non-vanishing of Donaldson invariants on closed symplectic manifolds. Well, there's this conjecture of Witten, which is that the Donaldson invariants should basically encode the same information as the Seiberg-Witten invariants. The problem is that it's a conjecture. But it turns out that various cases of the conjecture have been proven. And what we have to argue is that, in fact, we can embed our analog of the Stein manifold into a closed symplectic manifold for which the conjecture has been proven. So that we use Witten's conjecture, in that case, and Taubes' result to show that the Donaldson invariants are non-zero, and then from there the proof is very similar. Okay. So let's go to lunch early. Thank you.
Other questions?
Yes.
Can you say what the closed thing that you plug that into is?
Yeah. Maybe that's a good question for later. Yeah,
So maybe related, so you said that you can set the contact topology into flow to the other settings. How about the mixed invariant and informative invariant? Do they also understand isomorphism?
it's not known. Yeah, so the isomorphism between Heegard floor homology and monopole floor homology is not known to respect the cobordism maps. Should be true.